Assalamu alaikum, welcome everybody to Environmental Measurements and Statistical Labs. So this is our first lecture on statistical test for chemical analysis. In this part, we will include rounding, significant figures, interpolation, regression, and least square methods. So we will use all these things in tests for chemical analysis to represent our samples. Let's start with rounding. So what is rounding? Rounding simply it's making number simpler but keep its value close to what it was. So the result is less accurate but it's easier to use. Okay, so for example, if you have a larger number of 5 digits, for example 5 6 2 1 2 1, so but you want only to make this number first, so you just want to keep this one to be 5 6 0 0 0, so this means rounding, so make rounding to the less, it looks easier, but it's less accurate. Okay, so so first, how to make rounding? You should decide which the last digit you want to keep. For example, you want to keep this number. Okay, this number to keep. Then look at the next digit. So if the next digit is less than 5, so you will keep it as 0. This is called rounding down. But if it's larger than 5 or larger, so if the next digit is 5 or larger, so then it's called rounding up, and you will add this value to the next one. So for example, you want to have the rounding to 5, so 6 here is larger, okay, than 5, so it will be 6 0 0 0 0. Okay, this is let's test. We want to round 74 to the nearest 10. Okay, so check the 4 is less than 5, so then the result will be 70. Perfect. Then we want to round 86 to the nearest 10, so 6 is 5 or larger, so it's larger than 5, then the number should be 90. Perfect. Let's take more examples. Now round 3.1425 to the nearest thousands. So we want to nearest thousand. This is nearest thousand. That means here. Okay. So now we'll keep 2. Okay. Check 5. 5 is should be rounded up to exactly. Now another example. Round this number to the nearest hundreds. What does it mean by hundreds? We should keep this number, this decimal. So check 2. 2 is less. Okay, so then is rounding down. Now we want to round it the same number to the nearest tenth. Okay, so check 4. 4 is less than 5, so it should be 3.1. Perfect. Okay, let's take this example. Round this number to the nearest 10. So nearest 10th. Okay, check 7 is larger than 5, so we can make it 1.3. Now, let's talk about significant figures. What does it mean by significant figures? So, significant figures are, or it is known as significant digits of any number, is an indication of precision. Okay? So, the more significant figures, the more precise is the value. In other words, significant figures provide an indication of uncertainty in the value. So if you have larger significant figures, you have more accurate number. Okay, so let's take this number 1. If you have 1 1. So I can say the range is between 0.5 and 1.5. But here, zero point 0.5 is included value and 1.5 is called excluded value, because as we said, 1.5 we rounded up to the next value, but excluded does mean any value less than 1.5. You can say 1.4 99999, so it's less than 1.5, but 0.5 is included. So you can assume this we have a wide range between 0.5. If I said I have 1 as one significant digit, we have one significant figures for 1, that means I have this range between 0.5 and 1.5. Okay, so now say I have two digits, two significant figures, 1.2. Now the range become less. So I have 1.15 and 1.25. Okay, this is my range. So just I included one another figure here. So now I have two significant figures. Then the range become less. Suppose that I added 3 next to 2. So I have 1.23. Now the range become less. So I have 1.225 and 1.235. Okay. So, and so on. If you have 1.35, then my range is 1.2295 and 1.235. So you can see the uncertainty become less, or the range become less, as I have more significant figures. Okay, so when you say you have measured value, remember that this significant figure is used for measured value, is not used for counted value. Okay, so 1 means you are not sure about this value. This value may be 0.5, maybe a range between 0.5 and 1.5. Okay, so it's also used in scientific notation. Okay, so for example, you have this value. Okay, so this value with how many zeros? 1, 2, 3, 4, 5, 6, 7, 8, 7. We have again 1, 2, 3, 4, 5, 6, 7, 8. We have 8 zeros. Okay, so it has only two significant figures. So the number, that means I can assure this value only, but I can't assure the other values. So they can represent it in terms of significant notation as 1.2 times 8 8 powered 10 powered 8. So this means the range of uncertainty is between 1.15 included and 1.25 times 10 of power 10 power 8 excluded. So you can expect I have a huge range between both numbers. Okay, so here we can say for example this 1.2. Okay, so we have two only significant figure, so this is my range. Okay, but as I have more digits, okay, I have less range of uncertainty, and so on. Got it? Okay. Now, if that quantity is counted rather than measured, for example, you have 3 apples. So the number is known precisely because you are sure that they are, for example, if you have 3 apples, they are 3. You can't say they are 2.5 to 3.5. We know it's exactly 3 apples, so it's pure integer. So how can I represent it in terms of significant figures? It's not a range, so the value is implicitly contain infinite number of significant figures because you are sure that they are 3, exactly 3. Okay, so 3 counted apples, it means 3 dot infinite numbers of zeros. So now let's say let's take this concise rules. Okay, so how to determine the digit not significant figures for any number. First, you have to start from non-zero from the left. Okay, for example, we have 0, 5, 2, 5, 6, 0. Okay, let's take this significant figure. How many significant figures I have? Okay, so first start from non-zero. So we'll start from here. Okay, 1. Then if there is decimal point in the number, then include all digits until the last right digit. Okay, if it's 0 or non-zero. So now if it's non-zero, if there is no decimal point, then include all digits until the last non-zero digits. Okay, so now suppose that we have this number. Okay, again it doesn't include any decimal, so I should count from non-zero until to non-zero as well. So I have 3 1 2 3, this is 6 and this is 0. Let's make it clear, this is 0. Okay, so 1 2 3 4, so I have 4 digits, 4 significant figures. Okay, so I can represent it as 5.2 5 6 times. So now I can count 1 2 3 4 times 10 power 4. Okay, example, find the significant figures for this number. Okay, now we said from the left we should start from non-zero. So this is my first significant figures. And since here I have a decimal, so I should count all numbers, 0 or non-zero. So here's 1, 2, 3, 4. So I have 4 significant figures. Okay, so here these zeros are not counted. Then I have all non-zero numbers should be included, and here 0 of number also are included as significant numbers. Why? Because I have decimal. Okay, finally we have 4 significant digits. Okay, scientific notation is a method to represent significant figures for numbers, and it's always written between 0.5 and 10. Okay, so your number shouldn't increase less than 0.1, shouldn't more than 10. So how to control the remaining numbers? By using a power of 10. Okay, let's take an example. So now suppose that you want to write this number in scientific notation. First, you have to decide how many significant figures in this number. So let's say 1, because we start from non-zero. 1, 2, 3, 4. Since I don't have any decimal decimal point here, so I should end only by non-zero. So I have 4. Okay, so 1, 5, 2, 3 times 10 power 3. But this is not in a scientific notation, because scientific notation should be between 0.1 and 10. So I should either make 0.15 or 1.523, okay, or 1.523. So here's I should compensate for the power. So this power, how many moved, is moved to 1, 2, 3, 4. So it will be here 7. Okay, here I moved for 3 digit only, so it should be 6. Okay, so we can say 1.523 times 10 power 6, or as we said earlier, 0.1527 times 10 power 7. So it also 4 significant figures. This one is not scientific notation. Okay, it's correct as a significant figure, but it's not correct as scientific notation. Also, this value is not correct. Why? Because they are larger than 10. Okay. Similarly, all these numbers are wrong if we can't call them scientific notation. So now let's take this example. Write this number in scientific notation with 1, 2, 3, 4, and 5 significant figures. Okay, so let's start first, count how many figures I have here. So I have 1, 2, 3, 4, 5. So if I write it in 5 significant figures, then it will be 3.500 times 10 power 5, okay, or 0.35 times 10 minus 4. So this is 5. Okay, now I want to represent it in terms of 4 significant figures. So I should make rounding down. So to make rounding down, check, okay, check, this is 5, this is 0, so this 0 is just, I will remove this 0, so it will be 3.450. Now if I want to make it 3 significant figures, check the last number, so just remove the 0. Now I want to make less less significant figures, or more uncertainty. Okay, so I can here check the 5. 5 should be rounding up, so it will be 3.5. Okay, now I want to make one significant figure, so now check 5, so it will be 4 times. So make sure that when you reduce the number of scientific notation, okay, it doesn't affect the value, okay, it just affects the precision, or how the sample is more or less accurate. Okay, so the sample here is less accurate, but you have the same value. Okay, so now if you have different 2 or 3 scientific notation or scientific significant figures, and you want to do calculation, like you want to plus or minus or multiply or divide, so how to make it with different scientific notation or different significant figures. So now let's start with multiple and division, okay, because it's much easier. Now when 2 or more quantities are combined with multiplication or division, so easily the final check the number, which one has the less significant figure. So the result should be the same number, same significant figures of the less number. Okay, here the number of significant figures of the result should be equal the lowest number of significant figures of any of the multiplicants or dividers. So for example, we have two numbers, we want to check them. So here, how many significant figures here? 1, 2, 3. How many significant figures here? 1, 2, 3, 4. So the result, whatever the value, should be only 3 significant figures. So when you calculate it, okay, on for example on your calculator, you will get this value. Okay, so but I need only 3 significant figures. That's mean 1, 2, 1, 2, 3. Okay, so check the 0. So 0 should I can make rounded down, so it will be only 15.3. Let's take a more complicated example. So I have how many numbers I have here? I have 2 significant figures. Here I have 1, 2, 3, 4 significant figures. Here I have 3 significant figures. So the result should be only 2 significant figures. So when you do the calculation on your calculator, you will have this value. But what I need is only 2 significant figures. So how to write it? So now 8 should be rounding up, so it will be 3.2 times 10 power 2 in terms of scientific notation, or if you want to write it in terms of normal significant figures, that's 320. Now, addition and subtraction. So addition and subtraction is more a tricky part. Here we have two rules, not one rules like division and multiplication. If all numbers have decimal, then the result should be the smallest decimal place. For example, if you have hundreds decimal and tens decimal, tens is less than 100 decimal. For example, you have x point xx and y point y. So which one is the less decimal? Y. So the result, my result should have only one decimal. This is when you have all numbers have decimal. Okay, because the rule, general rule, the result should be the least accurate number. Okay, or the you can reduce the uncertainty. So now if any numbers, if any of the numbers doesn't have decimal, okay, then the result should be the smallest significant figures, because if any number doesn't have a decimal place, that means you have a range of accuracy, okay, range of uncertainty, sorry. So here we should apply the smallest significant figures. For example, let's check this one. Now we have this number, all of them have decimal, okay, but the first number have tenth decimal and this have thousandths decimal, okay, so the result should be tenth. So I can when I do the calculation, I should have only two, so I should make rounding down, so it will be only one decimal point. Okay, so now let's check this one. Now all this number also have decimal. So how many significant figures here? 3. How many significant figures here? 1, 2, 3, 4. So the result should be only 2 decimals. So it be hundreds. Okay. So when you multiply them, okay, it has this value. Okay. So but we said it should be only 2, so we can round it down the 4 to be 2.78. okay, now let's go for addition to 1 if one of numbers doesn't have decimal. So now we add 500 to 1.234. Let's now, this is 500. How many significant figures here? Only one. So that means the range is from 450 to 550. Okay, but this value is excluded and this value is included. Okay, so you can assume how many range of uncertainty. It's almost 100. You have almost 100 uncertainty in your sample. So this value is 1 out of 100. Okay, so it doesn't affect the value. If you, for example, you put it, it doesn't affect the value. Okay, so the result will be the same, 500. Okay, because this value will not add a value to this range. Okay, so now let's apply the rule. Okay, how many significant figures here? 1. How many significant figures here? 1, 2, 3, 4. Okay, then we will use the less significant figures, 5. So the result should be only one significant figure, 5. Okay, so for example, this is the accurate result, but actually we should have only one significant figure, so it will be 500 as it is. Okay, now for multi calculations. If you have multi calculations like plus, minus, addition, subtraction, a lot in the same equation. Okay, so we should take the order of operation. Bid mass. What bid mass means? Bid P as in brackets. Then so you should make the order brackets, then exponents, then division and multiplication has the same order, and addition, subtraction have the same order. Okay, this is important in significant calculation. So for example, we have this number and you want to uh, calculate the results. So first you should start with brackets. You don't have brackets. Okay, then exponent. We don't have exponent, but we have multiplication here. So we have this part is multiplication and this part also is multiplication. So first calculate the significant figures for this part and then calculate the significant figure for this part. Okay, and finally you can do the addition for all number. So first it will be, because here we have as you can see, it will be 15.3 plus 51.75. okay, as you can see here, we have in this part three significant figures, so that's why the results here are three significant figures. Okay, now how many significant figures here? We have the list one is 4, so it will be 4. But now we can apply the summation. So summation here is we have one decimal, so the result should be only one decimal. The other way is to, if you have like a set of multiplication and division, you can look at your figures and always check the least significant figures. So you can choose it to be the final. So for example, here we have after you do your calculation, you can check which the significant figures here. 1, 2, 3, 4. Here's 1, 2, 3, 4. Here's 1, 2, 3, 4, 5. Here's 1, 2, 3. So the result should be only 3 significant figures. So you can write it here. Okay. So this is another way. So to write it in terms of scientific notation, it will be like this: 0.703. Okay. Or you can write it in 7.03 as well. It's fine because the range should be from 0.1 to 10. Okay, so any is correct and you have the same significant figures.